Okay, this is our review. I know I already have a little bit written in question one. We'll get to that in a second. So what we're going to do with this is go all the way through it. But some of these questions have an explain your answer piece. So I want to talk about that first. Then I want to talk about how I want you to use the video. Then we'll jump into all the questions. So for these explain your answer questions, what I want from you is sort of a logical path through the question. If you need to do work in order to answer the question, do that work. And some of that can contribute to your answer to the question. But what I want is how you're thinking through the question in order to do the work. I don't think a lot of them are just show your work questions. Number one certainly isn't. So pay attention, especially to the first one, of how I go through that. Let that inform how you're going to go through it as well. The second thing I want to remind you of is that when we're doing these questions, when we're doing these problems, I don't want you to just watch me go through all of them and absorb that information. It will be much more useful to you. It will be much better for your grade. It'll be much better for your learning if you at least try the question one time before seeing my explanation of the question. It does some stuff in your brain that's really helpful when you correct bad work or confirm good thinking, as opposed to just listen to me explain it. So that being said, let's go ahead and get started. So we have two groups of 5 men each, and they're pulling with a force of 900 newtons. If the rope doesn't move, what's the tension in the rope? Okay, so for this, there are 5 men on each team. So the first thing that we know with 5 men on each team pulling at 900 newtons is that each team pulls with 4,500 newtons. Now, that means I've got 4,500 newtons on one end of the string, 4,500 newtons on the other end of the string. So, for a string, for a rope, tension in the rope is the same all the way through, right? There's no place where the tension's not going to be the same for this little horizontal rope. Misspelled through, sorry about that. And if a team pulls on the rope with 4,500 newtons from Newton's third law, then the rope pulls back on that team, so it must pull, which is a tension force, with the same force of 4,500 newtons. So because of that, the tension in the rope is 4,500 newtons. So Newton's third law says, if I pull on a rope, the rope pulls back on me with the same force. So if one team pulls on the rope with 4,500 newtons, the rope pulls back with 4,500 newtons, and a rope pulling is tension. That's all there is to it. Number two, the term net force most accurately describes, mass and inertia are properties of matter that resist changes in motion, so it's not A or B. Velocity is the thing that causes displacement. To keep an object moving, that's also inertia. That's resisting a changes in motion. So what we need is the quantity that changes the velocity of an object. Now, another way to look at this is kind of define net force equals mass times acceleration. The way I like writing it is that acceleration is net force over mass. And so I want us to think about acceleration as a change in motion. Acceleration is a change in motion. My velocity changes, my acceleration changes. Net force is the thing that causes the change in motion. And it's net force. It's not individual force. It's the forces added together. That's the quantity that changes the motion. And then mass is the quantity that resists the change in motion, which is inertia. So by definition, I'm ahead of myself. By definition, the net force is the thing that changes motion. That causes a change, that makes acceleration happen. So number three, which of the following describes the tendency of an object to remain at rest or in motion with constant speed in a straight line? That's talking about inertia, which is, again, that quantity that resists changes in motion. Number 4 is a basic Newton's second law question. I know the net force, I know the acceleration, I want the mass. So if net force is mass times acceleration, mass is going to be net force over the acceleration. So that's going to be 10 newtons divided by 50 meters per second squared, giving me 0.2 kilograms. All right, number 5, this is another explain your answer thing. So again, a clear sort of logical walking through how to answer this question is what I want. The reason I'm doing questions like this is because on the AP exam, and we'll start to roll these out soon, not this test, but soon, it asks for a paragraph length response. That paragraph length response wants reasoned argumentation from one place to another, like I'm showing you with things like question 1, question 5. So let's go through it. So the answer is it's equal to the weight of the rock. When I throw the rock up in the air, the rock is a projectile. As long as it's in the air, it's a projectile. And the thing about projectiles is that projectiles, by definition, only have weight, or the force of gravity, acting on them. That's what makes them a projectile, right? The only acceleration they have is the acceleration due to gravity, because the only force acting on them is weight. Nothing else is touching them. It's just gravity slowing them down on the way up and speeding them up on the way back down. So weight does not stop acting on the projectile, even at the top. So the entire time the object's a projectile, even at the top when it stops and turns around and comes back down, the entire time it's a projectile, weight is acting on it. So then at the top and at every point, the only force, which means the net force acting on my object, is its weight at every point, even at the top. That's why it's equal to the weight of the rock. The net force is the same, pulling down towards the center of the earth the entire time. Number 6, a force accelerates a body of mass m. That same force applied to the second object produces 3 times the acceleration. So, net force is mass times acceleration. What we're going to do is make a change to the system to where the same net force increases the acceleration by a factor of 3. Acceleration and mass are inversely proportional, so if the acceleration goes up, the mass has to have gone down by the same factor. Another way of thinking about it is that if I have more acceleration with the same push, I have to have had less inertia, less resistance to a change in motion. So that gives me 1/3 of the mass. Question 7, another explain your answer. So let's answer it first, and then we'll kind of form the argument. This is showing a 2 kilogram object moving in a line, and I want to know which section corresponds to net zero force. Sorry that the picture's kind of in the middle there. So, sections 2 and sections 4 show me net force. Here's why. First point. Sections 2 and sections 4 have a slope of 0. That's the thing that I notice about them. The slope of a velocity versus time graph is acceleration, so we're pulling in something from the last unit. So if I have a slope of 0, I have 0 acceleration. 0 acceleration means 0 net force, which is what we're after right there. Number 8, a body moves with a constant speed in a straight line. Which of the statements must be true? So if it's at a constant speed in a straight line, the net force is 0. right? And again, constant speed means acceleration is zero. Zero acceleration means zero net force. It doesn't mean no forces act. It just means the forces that act balance each other out and they cancel each other out, giving me zero net force. All right, number 9 wants to know what weight is. The weight of an object is the result of gravitational force. Now, we calculate that by multiplying the acceleration due to gravity at sea level by it. But that's cheat, right? If I go someplace else where the acceleration due to gravity is not 9.8 meters per second squared, it would not be appropriate to use 9.8 anymore. That's an easy way for us to do it. But weight is caused by gravitational force. And number 10 kind of leads into that, right? So if we go to the moon, we have less gravity, which means we have less weight on the moon. So an astronaut whose weight on Earth is 600 newtons will go to the lunar surface. There's less weight on the moon, so his weight on the moon will be 100 newtons. But this question's tricky because it's asking about the mass of the man. And his mass doesn't change because that's just how much stuff there is. And if I didn't remove an arm from this man, then I didn't change his mass. Or if he didn't gain weight on the trip, I didn't change his mass. So what I want to know is the mass of this guy. So weight, the force of gravity, the result of gravitational force acting on an object, we usually calculate by mass times the acceleration due to gravity. So on Earth, his mass is going to be the force of gravity over g. So that's 600 newtons divided by 9.8 meters per second, or 61.2 newtons. Sorry, 61.2 kilograms. All right, the bird. And this is the question that you're going to remember when you leave this class, and probably not fondly, right? So a boy holds a bird in his hand. The reaction force to the weight of the bird is the force of the bird on the earth. So let's go through this explanation. Okay, action and reaction forces act between two different objects. So if the action is on the bird, the reaction has to be on something else, right? So that statement that action and reaction act between and on two different objects means that if the weight is on the bird, the reaction to that has to be on something other than the bird. So A and C are right out. So I know that action and reaction act between two different objects. Weight is shorthand. It's the force of the earth pulling on the bird. That's what weight is. So the reaction would be the force of the bird pulling on the earth. That's it. 12 is the same kind of question. Body of weight W is in free fall near the surface of the earth. What force does the body exert on the earth? Well, the weight is the earth pulling down on this body. So the reaction to that is the body pulling up on the earth with the same force, same size, W. Action and reaction have to be the same. 13 is another action-reaction thing. Sorry. They have to be the same size force. So number 13, also action-reaction. So we've got if the force with which the bat hits the ball is considered action, reaction is the reversal of that, or the ball hitting the bat. So we need those same two objects, but the force is now acting on the bat instead of the ball. So we have the bat hits the ball, and we need to find the force of the ball on the bat. That's action and reaction. Same two objects involved in the force, but action and reaction act on different things. First one's on the ball, second one's on the bat. All right, 14 is another explain yourself question. So the answer here is 20 newtons. Let's talk about why. First thing we notice is that it's moving at a constant velocity. And an object moving at a constant velocity, has acceleration of 0 and net force of 0. That's the first thing we know. So right away, by telling us that the object's moving at a constant velocity, we know the net force is 0. Second thing, with the net force equal to 0, all of the forces must be canceled out by other forces. All of the forces are balanced. So if I'm pulling forward with 20 newtons, if the forces are balanced, then the pulling force has to equal the frictional force. So if we look at a little free body diagram of just the x direction, I'm pulling forward with 20 newtons. It tells me it's on a rough surface so that there's friction. Friction is backwards. So if my forces are balanced, the forward force has to be equal to the backwards force. Friction is equal to 20 newtons. That's how we know that. Number 15, we have this block on an angle, and I want to know if the normal force is greater than, less than, or equal to the weight. If it were a flat surface, the normal force would be equal to the weight because the normal force completely balances the weight. But if I go on an incline and I tilt it up, the weight's going to accelerate and fall, so the forces aren't balanced anymore. And what's happening is weight is still straight down, but the normal force is up at an angle. Because of that, they don't exactly balance each other anymore. And the normal force is only balancing part of the weight. So the normal force is going to be less than the weight. So it's going to be less than the weight. So what we want to do, and it's only because a part of the weight balances the normal force. So if we look at a little free body diagram here, weight is straight down for my object. Normal force is up perpendicular to the surface. Pardon. So if we go ahead and resolve the weight, break up the weight into the part that's with the normal force and against the normal force is up. mg cosine theta, part of the weight is opposite the normal force, and part of the weight is down the plane. Because mg sine theta is only part of the weight, that means the normal force is equal to only a part of the weight. So it's less than that. So if the block is at rest on the incline, if I'm at rest, the kind of friction I have is static friction. So if I increase the angle of the ramp and we don't slide down, mg sine theta gets bigger because more of the weight is pointing down the plane, so static friction has to get bigger as well. So static, it would increase as the angle increases, or as the part of weight pointing down the plane against friction, so that's mg sine theta, increases. Another thing to talk about here with friction that's really important for us as we're reviewing for our test is that static friction will increase until the object breaks free, until we reach maximum static friction. So static friction sort of has a sliding value. It's as big as it needs to be until my object breaks free. Something we need to remember for static friction. For 16, this system is frictionless and at rest, and I want to know if mass 1 is greater than mass 2. So we're going to solve this 3 different ways. One is just kind of thinking through it. So in order for everything to be balanced, first, it's going to be less than, because only a part of m2g pulls down the plane opposite to tension. So only part of M2G opposes tension. And since the same tension pulls up on M1G, only part of M2G opposes all of M1G. So that means mass 1 can be less than mass 2. The other way of doing that is to take in and sort of draw our free body diagram. That's mass 1, tension's up, mass 1G is down. And then for mass 2, if we draw that free body diagram, free body diagram looks like that. Resolved free body diagram, we've got M2G cosine theta into the plane, M2G sine theta down the plane, and the normal force up. So if we straighten both of those things out to where they're all in a line, where the acceleration would be in the same direction, we see M1G pulling to the left, tension pulling to the right on M1, and for mass 2, tension pulling to the left, normal force up, M2G cosine theta down, and M2G sine theta pulling to the right. Normal force and M2G cosine theta balance each other out. Tensions cross out. And so that leaves me with M1 plus M2 in the middle. M2G sine theta pulling to the right, M1G pulling to the left. And so if my acceleration is 0, then M1G is equal to M2G sine of theta. And the last way that we're going to look at this is the quote-unquote hard way, where we take our free body diagram and we write some Newton's second law equations. So mass 1 is M2 sine theta is less than 1. So we know that the acceleration equals 0 for both of these objects. So before we can write Newton's second law, we decided it would be helpful to write in the positive and negative signs for each force so that we knew if a force was positive or negative. So we're going to say tension on mass 1 is up and positive. M1G is negative. Tension on mass 2 is negative. Normal force on mass 2 is positive. M2G cosine theta is negative. M2G sine theta is positive. Just how everything's moving. So if for mass 1, I look at the net force in the y direction, I've got tension minus M2G cosine theta. If I look at mass 2, in the x direction, I've got M2G sine theta minus tension. That's what I have in the x direction. And in the y direction, my net force is normal force minus M2G cosine theta. Now we need to go through and decide if my net force is equal to MA or 0. Since the acceleration is 0 for the entire problem, I'm just going to set them all equal to 0. So t minus m1g equals 0. M2G sine theta minus t equals 0. And normal force times m2g cosine theta equals 0. So in the first equation, because tension minus m1g equals 0, tension is equal to m1g. In the second one, because m2g sine theta minus tension is equal to 0, m2g sine theta is equal to tension. And in the third one, the normal force is equal to m2g cosine theta. So if we're going to be looking at finding the relationship between m1 and m2, I know that tensions are equal to each other. So from these two equations, I'm going to set them equal to each other, right? So that tells me that m1g is equal to m2g sine theta, and that's just what we had before, telling me that m1 is less than m2. All right, so what we have here for our last part is a question from the 2017 AP exam. It's an experimental design question. I thought I'd walk through this with you all as part of the review for our test, because it's part of knowing what's going on here. This question can be found on the College Board's AP Physics 1 website with a couple of student samples on how people did on this, as well as a rubric on how to grade it and what they were looking for as the College Board. So in this question, a student wants to determine the coefficient of static friction between a long, flat wood board and a small wood block. So it's up to you to describe the experiment and what they want you to do there, and this equipment usually found. So first thing is to draw a diagram of the experimental setup. So it's static friction, which means for static friction, the object doesn't move. That's important. So we're going to have the block sitting on top of the board on the bottom, block on the top, and then we're going to pull it with a spring scale or a force sensor or something that's going to tell me the force of the pull. Right? So that thing measures the pulling force. So indicate each quantity that would be measured. Yeah, so we're gonna pull, and it's gonna measure my pulling forces. So I've indicated that, and I've said the equipment that I'm going to use is the spring scale. Additionally, we just kind of want to talk about the fact that I'm gonna need to use a balance to find the mass. So that's my basic setup, right? I got a block. I'm gonna pull it with a spring scale. Part two is to describe the procedure. So how I'm going to use that measurement how I'm going to use that equipment to get the measurement. So use a balance to find the mass of the block. Step one is to mass the block. I need to know how much its mass is. I'm going to use a balance for that. Right? So I'm being explicit about what I'm measuring and the thing I'm using to measure it. Next thing I'm going to do is put the block on the board, and I'm going to pull horizontally until it just breaks free. So what I'm doing is slowly increasing my pull, which is going to be equal to the static friction on it, until my pull exceeds the static friction. And so I'm going to record the maximum pulling force there. And it says, including any steps to reduce experimental uncertainty. Most of the time when we're reducing experimental uncertainty, we're going to change something and repeat the measurement. So this time we're going to add a little bit of mass to the block and pull it again. The reason we're going to add mass to the block is because adding mass to the block doesn't change the two surfaces in contact. So the coefficient's going to remain the same, but the normal force and probably the frictional force will go up because of that. So B is get an equation for static friction in terms of what I measured. So from the formula sheet, well, let's look at the free body diagram first. I have the force of the pull in one direction, friction in the opposite direction, weight is down, and normal force is up. Now from the formula sheet, when the block breaks free, the acceleration is still different. The acceleration is still 0, so the net force equals 0. That's an important piece. So the net force in the x direction is the force of the pull minus the force of friction. And since the acceleration is 0, that's going to be 0. The net force in the y direction is the normal force minus the weight. Since the acceleration is 0, that's also going to be 0. Now, the first equation tells me that the force of the pull is equal to friction. The second one tells me the normal force is equal to the weight. From our formula chart, we can know that the coefficient of friction is the force of friction divided by the normal force. But that's not a derived equation that has anything to do with my measurements, because what I measured was the force of the pull, which we said was equal to the force of friction. And I measured the mass, which I can calculate the weight with. So my equation for the coefficient of static friction for my experiment is my maximum pulling force divided by the weight of the object. Now, the next part of this is a physics class wants to test the hypothesis that coefficient of static friction equals the coefficient of friction between the board and the block. Each group determines coefficients. They put them in a table. They take some averages. So what we see is something's a little weird about group 5. The average comes out to the same But if we ignore group 5, then the averages aren't the same, and the coefficient of static friction is more than the coefficient of kinetic friction. That's what we see in the data. So if we go to part C, based on these data, what conclusions should the students make about the hypothesis that the coefficients of static and kinetic friction are equal? So they are not equal because even though the averages are equal, lab group 6 is an obvious outlier. Another way to think about it is every group except for that group shows that mu k is less than mu static. Every other group supports the fact that static and kinetic are not equal. And in fact, group 6 supports that as well. So even though their averages are equal, no group got data showing that coefficient of static friction was equal to coefficient of kinetic friction. Part D, we're going to add a metal disc to the top of the wood block. Now it's twice the mass we had before, and I want to know if the coefficient of static friction between the block of the board increases, decreases, or remains the same. We've already kind of talked about this. It remains the same because the coefficient of static friction is determined only by the surfaces, or the roughness, the surface roughness. Adding mass increases the normal force, which will increase the friction, but mu is the same because mu depends on something else. It depends on the surfaces, and if the surfaces don't change, then mu does not change.